we go. Okay, so welcome to the Trig review workshop on Trig identities. A lot of people hear identities and they picture this incredibly long list of things to memorize. And I tend to think of two identities. Now, it's going to vary a little bit with your professor, but for first semester calculus, I really believe if you have a working knowledge of these two trig identities, you've got what you need for first semester calculus. There are a few more that we'll add on. I know some of you are here who are taking 3B. There are a couple more that get needed in 3B. And for those of you in pre-calculus, we cover all of them because, of course, pre-calculus is preparing you for all of those semesters. But I want to emphasize that I said working knowledge. So I didn't say you just got to memorize two things and then you're good to go. You've got to understand those things and be able to see the connections with other things. So I'm just going to start by drawing a picture of our lovely unit circle here. And I'm in the habit when I label my circle, I label the horizontal axis as the capital X axis, and I label the vertical axis as the capital Y axis. Now, there's really nothing super significant about that. It's just that sometimes we call the angle X. Sometimes we call the angle theta, but sometimes we call the angle that we're going to plug in little x. And I don't want to confuse the angle little x with capital X, the distance on this horizontal axis. So I'll probably just use theta to avoid that confusion in its entirety in this workshop. But I just wanted to explain my notation. And I'll often say it's the capital X value or the capital Y value. And that's just to emphasize it's the X or Y value on these axes on which I've drawn the unit circle. Now, if I draw an acute angle theta in standard position, if it's an acute angle, it's between 0 and pi over 2, or in degrees, it would be between 0 and 90 degrees. And it end up in quadrant 1 where everything is positive. And this picture is incredibly powerful because this picture is going to give me the unit circle definitions of my trig functions. If I know SOHCAHTOA, which gives me the right triangle definitions, it gives me the unit circle definitions because this angle intersects the unit circle at a point capital X, capital Y. If I draw a perpendicular to the x-axis, I've created this beautiful right triangle here. Okay. Now, since this is the unit circle, I know that the hypotenuse is 1 because the hypotenuse is a radius of the unit circle. Okay. And then I know that to get from the center to this point, I came over x and up y. And if I'm in quadrant 1, x and y are both positive. And so they are actually actual side lengths of this triangle. If I'm in any of the other quadrants, x, y, or both of them are going to be negative, I could still label things and view them as signed sides. But if I have an acute angle, I can actually view them as actual side lengths. So one thing that we use this for, and this was actually covered in the last trig review workshop, so I won't go through all of it, is sine of theta. I know just from SOHCAHTOA, the right triangle definitions, that sine is opposite over hypotenuse. Well, the opposite side is y rather, and the hypotenuse is 1. And so sine of theta is 1. So if I ever forget the unit circle definition, I can get it back using this picture. Okay. What I want to use that picture for today is to derive some really important trig identities. Okay. Okay, so there are the reciprocal identities. I view those as basically just definitions. I don't view those as additional identities that you need to know. You do need to know that by definition, secant of theta is the reciprocal of cosine of theta, for example, and cosecant of theta is the reciprocal of sine theta. And cotangent of theta is the reciprocal of tan theta. Of course, each of these three equations comes with a partner because the reciprocal of the reciprocal is the original. So cosine theta is the reciprocal of secant of theta. Sine of theta is the reciprocal of cosecant of theta. And tangent of theta is the reciprocal of cotangent of theta. You really don't think of these so much as, like I said, as new identities, so much as just the definitions. Although I do need to point out something that's kind of interesting about identities. As long as I'm working just with the right triangle definitions, I can take cotangent being the reciprocal of tangent to be the definition of cotangent. Once I expand to the unit circle definitions, so that I'm able to apply trig functions to almost any angle, as long as I don't get a 0 in the denominator, the trig functions are defined at any angle. There are places where tangent is 0, so I can't take its reciprocal, and cotangent is undefined there. But there are also places where tangent is undefined, which means I can't take its reciprocal, because what's the reciprocal of undefined? But cotangent is actually 0 at those places. So an identity is a little bit different from just a definition. An identity is an equation that is always true as long as both sides are defined. So, for example, sine is always defined. Cosecant is not always defined, because when sine is 0, its reciprocal cosecant is undefined. Well, when cosecant is undefined, this side, it doesn't make sense, and so the identity doesn't hold there. That doesn't make it false. The definition of an identity is something that's always true when both sides are defined. So you do need to check that both sides are defined if you're using your identities. But what the identities allow us to do then is they just give us options for how we're going to write things. And we'll see as we start working with these that sometimes those options make it easier to do various things. We've got a trig expression that's written a certain way. We've got to do something with it. That seems like a really hard problem. And then we use an identity and we rewrite that same trig expression a different way. And suddenly what we have to do is a lot easier. So that's the advantage of the identities. Okay, so these really just follow from the definitions of the trig functions. But if I take a look here, if I just continue with my SOHCAHTOA, cosine of theta would be x over 1, because it's adjacent over hypotenuse, which is x. And tangent of theta is opposite over adjacent. That's going to be y over x. Oh my goodness. That's sine of theta over cosine of theta. So that follows directly from this picture. And although this picture was drawn using an acute angle, the unit circle definitions that we derive using the acute angle in right triangle trigonometry, these results actually are the unit circle definitions that we apply to all angles. So this identity, I actually get from that picture. If I ever forget it, as long as I remember, oh yeah, I can write tangent in terms of sine and cosine, but I don't remember exactly how. If I can draw this picture, I can actually figure out how, which is kind of nice. So tangent can be written as sine over cosine. Now, I mentioned that you want to have a working knowledge, welcome, a working knowledge of these identities. And one thing that means is that you can derive other identities from them. So if tangent is sine over cosine, cotangent.
Cosine of theta over sine of theta.
It's going to be the reciprocal of tangent. So it would be cosine of theta over sine of theta. One thing that's super nice about these are what we call the quotient identities. With these, we can now write all 6 trig functions in terms of just two. I can say tangent is sine over cosine, cotangent is cosine over sine. And of course, secant and cosecant are just the reciprocals of cosine and sine, respectively. That's really important for those of you, particularly in pre-calculus, where you spend some time proving identities. Sometimes when you're trying to prove an identity, you're looking at this formula and just things start swimming all over the page because you've got 6 different trig functions. Well, when I don't see something else to do, if I see something else to do, maybe I'll do it. If I don't see anything else, I write everything in terms of sine and cosine. And to me, that simplifies the problem because now I'm down from 6 trig functions to just 2. And they're the 2 that I'm most familiar with. So that's a really powerful thing right there. So I mentioned that I feel like for first semester calculus, you really just need a working knowledge of 2 identities. Not counting these because I count these as basically definitions or following right from definitions. This is one of them. Don't bother to circle that one because this one follows from this one. So if you have a working knowledge of this, it comes as a pair. Tangent is sine over cosine. Therefore, the reciprocal of tangent, which is cotangent, is cosine over sine. Just going to check the chat, make sure there aren't any questions. Not seeing any, so. Any questions from anybody here or in the chat? Excellent. So just to free up some board space here, I'm going to erase these, but I'm going to keep this picture up. Because this picture is going to give me my next incredibly powerful trig identity. Okay. Who remembers the Pythagorean theorem? Okay, so a lot of folks do remember the Pythagorean theorem. Basically says anytime you have a right triangle. Pythagorean theorem. If I have a right triangle, and I'm going to label the 2 legs A and B, and the hypotenuse C. Now it is important, it has to be labeled with the hypotenuse C if I'm going to write it this way, but it's leg squared plus the other leg squared equals the hypotenuse squared. If I really wanted to be tricky, I could label one of the legs C, and then it would become A squared plus C squared equals B squared, and everybody would be like, no, math has changed. But we'll usually label the hypotenuse C. Okay. Well, if I look here, I've got a right triangle. So x squared plus y squared equals 1 squared, which of course is just 1. X squared plus y squared equals 1. That is actually the equation of the unit circle. What that means is if I take a point that's on the unit circle and I plug in its x and y value, it's going to make that equation true. And if I take a point that's not on the unit circle and I plug in the x and y value, it's going to make that equation false. Okay. And I see it from this right triangle. So if I point over here, like so, that would maybe correspond to an obtuse angle. That still intersects the unit circle at a point that has an x and a y value. The difference here is that since we're in quadrant 2, my x value is now negative. Well, I can still draw in a triangle. And I can still label the sides. Now, sometimes people label these signed side lengths, so they allow for negative numbers as they're labeling things. That's a perfectly legitimate strategy, although I don't think it's particularly helpful when I'm working with variables. The reason for that is we're so used to with numbers. The reason that I know that that's a negative number is because I see the negative sign in front of it. I'm a math teacher. I know these things. When there's a negative sign in front of a number, it means that number is negative. But when I write a variable, I don't know whether that's positive or negative. I can't look at whether there's a plus or a minus sign in front of it. You've probably solved equations before where x was -3. And you don't say, but there was no negative sign in front of X, so that must be wrong. A variable can be negative without there being explicitly written a negative sign. So what I like to do when I have variables is I just choose to label everything as the actual positive side lengths. So I would just label this side as the absolute value of X. Okay. And notice that's going to work in any quadrant. I could label this as the absolute value of X. When it's positive, the absolute value doesn't change anything. But when it's negative, it just changes it to a positive. I'm going to label this as the absolute value of Y. In quadrant 2, the absolute value isn't necessary because Y is positive anyway. But I could draw a triangle in any one of the 4 quadrants and label the actual side lengths as absolute value of X plus absolute value of Y equals 1. Or again, 1, sorry, that equals 1. If I apply Pythagoras, absolute value of X squared plus absolute value of Y squared equals 1 squared. And the absolute value becomes unnecessary because when I square something, whether it was positive or negative, it's going to become positive. So this equation, X squared plus Y squared, is actually the equation for this entire circle, not just that first quadrant. Okay. But I know what X and Y are, because X was cosine of theta. So this is cosine of theta squared plus sine of theta squared, because Y was sine of theta, is equal to 1. And we call that a Pythagorean identity. And this is the primary one that we see. Usually I'm going to make a notational change when I write this. I'm going to write this as cosine squared theta plus sine squared theta equals 1. That's because when I'm writing fast, I tend to get sloppy and I sometimes accidentally drop parentheses. If I were to just drop the parentheses here, that would tell me square theta and then plug into cosine. This parentheses is actually necessary to say I'm not squaring the angle, I'm squaring cosine of the angle. Writing it this way, it's clear that I'm squaring cosine. And cosine doesn't make any sense unless I plug something into it. So I know plug in cosine, plug in theta, take the cosine, and then square that result. But this way I don't have to worry about writing the parentheses. Sometimes, particularly when this notation is new to you, it's worth the time to actually rewrite things that way to be able to see things more clearly. But I'd encourage you to try to familiarize yourself with this because you'll see it a lot in textbooks. And if you're starting to write fast, most of us do drop a parentheses now and then, and it can actually change the meaning. Okay. So now I can show you, before we move on to the other identities that follow from this one, I can show you pretty nicely why these identities can be so helpful. Okay. Let's suppose I want to take the square root of 1 minus cosine squared of theta. Now, at first glance, that looks kind of tricky because square roots do not distribute over subtraction. I can't just take the square root of each piece and subtract the results. Just check this out. Square root of 25 minus 9 is definitely not the square root of 25 minus the square root of 9. This would be the square root of 16. This would be 5 minus 3. Square root of 16 is 4. Last I checked, 5 minus 3 was not 4. So that's a nice, easy demonstration. If you're ever tempted to distribute a square root over addition or subtraction, don't. Unless you think that 4 and 2 are the same number, then rethink. Okay. So it's tricky anytime I have an addition or a subtraction problem under a square root. Does anybody want to suggest how I could rewrite this to make this problem easier? So I could factor this. It's a nice suggestion. I could factor this as the square root of 1 minus cosine of theta times the square root of 1 plus cosine of theta. That is a totally legal thing to do. And I would rather have multiplication under a square root than addition and subtraction, just because the square root does distribute over multiplication. The problem is that I have one subtraction problem and one addition problem. So I'm not sure that's actually going to make it simpler. It's certainly something that I could do. And very often when I see a difference of two squares, it's something that I try to do. But I'm not convinced it's going to make this simpler. So does anybody see a way that we could use our identity here to rewrite this? I'm going to look in the chat to see.
You could also subtract cosine squared theta from each side, and then you get sine squared theta equals 1 minus cosine.
Yeah, that I think is going to be simpler, because if we do this, it's totally legal, but it doesn't get me closer to being able to evaluate the square root. But if I take a look at this identity here, I can rearrange this. Sine squared theta is 1 minus cosine squared theta. I just followed his suggestion and subtracted cosine squared from both sides of the equation. So I can say, oh my goodness, this is the square root of sine squared of theta. Now that looks like it's going to be easier to evaluate. I will caution you, it looks deceptively easy. Okay, I'm going to evaluate it and I'm going to make a mistake. And I want to see if anybody can catch me, and then we'll fix the mistake. I'm going to say that the square root of sine squared theta is sine of theta. And I am wrong. Can anybody tell me why I'm wrong? This is tough.
The square root applies to theta.
No, the square root actually applies to sine of theta. So it applies to the number that's under the radical, and the number under the radical was sine squared of theta.
Okay. Since you're getting rid of the squared with the root, I guess you recognize that the theta should be under its own root, or is that incorrect?
No, because theta is just the input to the function.
Okay.
All trig functions spit out some trig ratio. For sine, if it starts out in a right triangle, it's opposite over hypotenuse. Uses the unit circle definition, it's the ratio of y to 1. So it just ends up being the y value. So basically, I would draw my angle, I would pick out the y value. It's the thing that I'm squaring, not squaring the angle that's here. Okay. I will give you a hint. Can square roots be negative? Can principal square roots be negative? I should be more specific. Yeah, this symbol means the principal square root, which means it's not negative. So for example, the number 4 has 2 square roots, 2 and -2. But when we write square root of 4, that symbol means the principal square root. So it says it's not just any old number I can square to get 4, it's the one that isn't negative. So it's 2. So this side of my equation is never negative. Anytime you see the square root symbol written, it is not negative. Can sine be negative? It can't, because sine is the y value where we intersect the unit circle. So if my angle happens to land in quadrant 3 or 4, that y value, that sine of theta, is going to be negative. So I have to be careful here. I have to just say it's the absolute value of sine of theta. That way, absolute value is negative, never negative. Principal square roots are never negative. But I think we can agree that even though we did have to include the absolute value here, the expression absolute value of sine theta is simpler than the square root of 1 minus cosine. So it allowed us to do a calculation that we maybe couldn't have done otherwise. Of course, if I know what quadrant theta is in, I'll know whether sine of theta is positive or negative, and then I can take things one step further and evaluate the absolute value, which is kind of cool. Okay, So this Pythagorean identity is the second of the two identities that I think are most important for success in first semester calculus. Now, don't go running to your first semester calculus teacher and say, Carla said we only have to know these two. That would be misquoting me. I said, these are the most important. And I know from my class, if you have a working knowledge of those two, you're going to be good. There are a few other identities we use in my class, but we use them rarely enough that I provide them to the class when we use them. Other professors might have different standards and require you to know them. So you always want to check, are there formulas you'll give us? What formulas do I need to know? But the quotient identity, tangent is sine over cosine, which gives us the luxury of writing all 6 trig functions in terms of sine and cosine. And this Pythagorean identity are the ones that are going to be most often used. Once again, I said we need a working knowledge of this because there are actually 3 Pythagorean identities. This is the first one, and there are 2 more. But if I know this one, I don't have to memorize the other 2. And I will tell you, I have actually taught pre-calculus and first semester calculus, and I think second semester calculus, without having the other 2 memorized. Now, I've taught it for long enough that I've accidentally memorized them. So at this point, I can no longer stand up here and say, I'm proud to tell you that I do not have the other 2 memorized. I actually do, but I swear I didn't do that intentionally. But when I didn't have them memorized, I didn't go over and look at my notes when I needed to use them. I figured them out. So I had them at my fingertips, just not at the tip of my tongue and in my brain verbatim. Here's the basic idea. There are 6 trig functions. When we write them in terms of sine and cosine, they sort of come in 3 pairs. Sine and cosine are one pair. They're the 2 that we don't write as fractions when we write them in terms of sine and cosine. Okay, they're the 2 that are always defined, and we don't write them in terms of fractions. But if I write the others in terms of fractions, let's just do that. Fractions that involve sine and cosine. So I would say secant of theta is 1 over cosine of theta, and cosecant of theta is 1 over sine theta. Those are actually the definitions of secant and cosecant. Throw in our quotient identities. Tangent of theta is is sine of theta over cosine of theta. And cotangent of theta is equal to cosine of theta over sine of theta. So when I write them in terms of sine and cosine, secant and tangent have something very important in common. They both have cosine in the denominator. Now, one consequence of that is that they're undefined at the same places. Okay. Similarly, cosecant and cotangent have something very important. They both have sine in the denominator. Again, a consequence of that is that they will be undefined the same places, which is wherever sine is 0. But another consequence of that is that there are a lot of identities that involve secants and tangents, taking advantage of what they have in common, or cosecants and cotangents, taking advantage of what they have in common. So let's say I wanted to get to the identity that involved secants and tangents. So there's a Pythagorean identity. And Pythagorean identities always involve 2 different trig functions squared and the number 1. Okay. And this is the primary one. I want to get to the one that involves secants and tangents. So what I'm going to do is I'm going to start with this one, cosine squared theta plus sine squared theta equals 1. I'm going to divide both sides of the equation. And remember, that means I'm dividing every term of the equation by cosine squared. I chose to put cosines in the denominator so I could talk about secants and tangents. And I squared them because the trig functions that I have on the top were squared as well. But now I can simplify it. It's cosine squared over cosine squared.
Well,
That would be 1. Notice this I could rewrite as sine of theta over cosine of theta squared. Because when you square a fraction, you square the top and you square the bottom. Same thing here. I could write this as 1 over cosine of theta squared. Because if I square the 1 on top, I get 1. And if I square the cosine on bottom, I get my cosine squared. How? What's another name for sine of theta over cosine theta? Tan theta. So this second term is tangent squared of theta. And the reciprocal of cosine is secant. So this other side of the equation is secant squared theta. So 1 plus tangent squared is equal to secant squared. Use that all the time in calculus. Use it an awful lot in second semester calculus in particular, I'm thinking of. And I'm pretty sure I taught that class before I had memorized this. Somebody taught me an annoying mnemonic device that stuck in my head. Now I can't get it out of my head. So I haven't memorized. So I used it so often that I just sort of remember it. I would just say, oh, we need the Pythagorean identity that involves tangents and secants. So I would write the one I knew, which was cosine squared plus sine squared equals 1. I would divide through by cosine squared, and I'd be like, yeah, 1 plus tangent squared is equal to secant squared. So this one follows directly from this one, which is kind of. Now, what I want you folks to do is almost exactly the same, except you're going to divide through by sine squared, because there's a third version of our Pythagorean identity, and that's the one that gives me a relationship between cosecant squared and cotangent squared. So your job is to start with the basic Pythagorean identity, divide through by sine squared, and see if you can get the third version. I'm going to stop the video while you're working on that. So I'll start it up again when we go over this, but just take a few minutes, whether you're here or at home, and try to work that out. Let's see, how do I stop the video? Awesome. Okay. So again, I'm starting with my basic one, just cosine squared theta plus sine squared theta equals 1. I'm dividing through by sine squared theta. And if you're comfortable saying, oh, cosine squared over sine squared, that's cotangent squared, totally fine to go right to that. If it helps you to see it, to write that as cosine of theta over sine of theta quantity squared, if that helps it make more sense to you, it didn't take me very long to write that. If it makes it stick in your brain better, it's worth the time to write that. So you got to sort of know yourself for how much you're going to take time rewriting things. This would be plus 1. Again, some of you might be comfortable going right to cosecant squared. Others of you might feel more comfortable if you first write that as 1 over sine of theta squared. However I get there, cotangent squared theta plus 1 equals cosecant squared theta. So that's my third Pythagorean identity. But really, the one you need to know is this one. And you don't even have to memorize this one if you know this picture and SOHCAHTOA. I mean, it's incredible. It's just sine is opposite over hypotenuse. Okay, so it's y. Cosine is adjacent over hypotenuse. Okay, so it's x. Tangent is opposite over adjacent. Oh, it's y over x. That gives me this. X squared plus y squared equals 1 gives me sine squared plus cosine squared equals 1. It's all in that picture, which is just those definitions. So it's kind of amazing, I think. The definitions of trig you know, when you're first presented them, it's sort of like, why are we doing this? And then maybe you see a little bit of, oh, similar triangles, okay. So if I can sort of measure the angle, I can figure out how tall that tree is or something like that. But there's just so much richness in these definitions. And it's kind of amazing that people discovered it, but I think it's pretty cool. Okay. Any questions on the quotient identities, which are these two, just writing tangent and cotangent in terms of sine and cosine, or the Pythagorean identities? Okay. Like I said, those are the ones that are going to be used most often in first semester calculus. In my first semester calculus, if you have a working knowledge of those, you will not need any other identities. There will be a few others that we use, but we'll use them just once or twice, and so I'll provide them to the class when we do use them. I am going to go over a few other identities that get used an awful lot in second semester calculus. And again, those of you in pre-calculus, we're preparing you for everything. So you'll see these a lot in pre-calculus. You'll see them maybe like once in first semester calculus, and then a lot in second semester calculus. Okay. Start with the sum formulas for sine and cosine. And I'm going to do something that's a little bit unusual for me, at least. I'm going to give you the formulas, and I'm going to give you a silly, dorky story. I love silly, dorky stories. That's not the unusual part. But a mnemonic device to help you remember the formulas rather than explaining. I usually like to show where things come from. Pythagorean theorem is just, or the Pythagorean identities is just the Pythagorean theorem, which we know from geometry. And can be demonstrated with some nice visuals too, if anybody wants to see that at a later time. But while these formulas can be derived, the derivation is pretty tedious. And so I sort of pick and choose what I'm going to memorize and what I'm going to figure out how to derive. If I'm using something a lot, I often accidentally memorize it. Like I don't have to draw this picture to get that tangent is sine over cosine because I use that so often. But sometimes when something is kind of tedious, I find it's worth memorizing. And I think for the sum formulas, I do. So here's how it works. Sine of A plus B. So this says, I think of A and B as angles. I'm going to add two angles to get a third angle, which is the sum. And then I'm going to plug that into. And it turns out it's sine A cosine B plus cosine A sine B. And cosine of A plus B is cosine of A cosine of B minus sine of A sine of B. It is possible to derive these arguments geometrically. Yeah, it's a fairly long and drawn out argument, and I don't think it particularly helps people to remember the formulas. But I have a dorky story to help you remember the formulas. I am so jealous. I wish I had come up with this story myself because it is just that level of dorky. I love it. Okay, this is actually courtesy of a former student of mine. She used to tutor over in the LRC, and she was tutoring somebody, and she said, and these words just came out of my mouth. I had this great story. So here's how it goes. It all comes down to the psychology, the sine and cosine functions. Sines, and you'll notice that one starts with an S. These are the social functions. So when sines are in charge of a party, they like to mix it up with the other trig functions. Okay, so they'll be going over and trying to make the cosines feel welcome. We're glad you're at our party. It's a very positive quality. Cosines, very antisocial functions. When cosines are in charge of the party, they stick with their own kind. That leaves the poor sines nobody to talk to but the other sines. Not only that, can you believe it? The selfish bastards put themselves first, and that is a very negative quality indeed. Okay. So those are our sum formulas. Okay. All right. We will use those in first semester calculus. You'll use those in the context of simplifying a difference quotient, because you'll have sine or cosine of x plus h, and you'll need to simplify that. Where we use them a lot in second semester calculus is not from these formulas directly, but what we can derive from them. Okay. So these two, I have a dorky story to remember. They give me a whole bunch of others that I use all the time. Okay. So I'm going to get to the doubling. So if I wanted to know what sine, I'll use that mark, what sine of 2 theta was, I'm just going to make the very brilliant, I think, observation that 2 theta is the same as theta plus theta. So I write it that way. I say, oh my goodness, I'm adding 2 angles and then plugging into sine. I think there's a formula for that. So I'm going to use the sum formula for sine. And all I'm doing is I'm replacing both A and B with theta. So that's going to give me sine of theta cosine theta plus cosine theta sine theta. But these two terms are actually the same, because it doesn't matter what order I multiply two things in. So that's just 2 copies of sine theta cosine. Okay, you guys get to do the next double angle formula. Figure out what cosine of 2 theta is. And again, I'm going to pause the video while you work on that. Just take a few minutes to work that out. I appreciate the LOL in the comments. Okay, so cosine 2 theta, I'm going to do the exact same thing. I'm going to say 2 theta. Well, that's just theta plus theta. So I'm going to come to the antisocial formula for cosines. And I'm just going to replace both A and B with theta. So that's going to become cosine theta and cosine theta minus sine theta sine theta. But then when I have 2 things that are the same multiplied together, I'm just squaring the thing. So this ends up being cosine squared theta minus sine squared theta. So that's my double angle formula for sine and for cosine. And it turns out the one that's actually more useful, I'm going to just copy them over here. So sine of 2 theta is 2 copies of sine theta cosine theta. And I want to just point out that that identity there actually involves 3 different trig functions. Because there's sine of theta, there's cosine of theta, and there's another sine, but of a different angle. There's sine of 2 theta. So there are 3 different trig functions that show up in that identity. Now, if I look at the double angle formula for cosine, there's cosine of 2 theta, and that's cosine squared theta minus sine squared theta. I am so grateful to my student who came up with that dorky mnemonic story for this, because when a formula involves a subtraction problem, I always struggle to remember what am I subtracting from what. I will often remember there's a formula and it's either A minus B or B minus A. Which one is it? Cosines are antisocial. They put themselves first. So, no mathematical insight there, but the psychology of the trig function is very, very helpful. Okay. This also involves 3 trig functions. I've got my cosine evaluated at 2 theta. I've got cosine at theta, which is squared. And I've got my sine of theta, which is also squared. The reason this one ends up being more powerful is because these trig functions are squared. I have identities that give me relationships between sine squared and cosine squared. So I could actually get this down to an identity that just involved 2 trig functions rather than 3. Remembering that sine squared theta plus cosine squared theta is equal to 1. I can solve for either of these. I can say sine squared theta is 1 minus cosine squared theta by just subtracting the cosine squared over. Subtract the sine squared over and say that cosine squared theta is 1 minus sine squared theta. Let's go ahead and use this one first. I'm going to just replace the cosine squared here with 1 minus sine squared. So cosine of 2 theta is cosine squared, which is 1 minus sine squared theta minus sine squared theta. But now I can combine these. I can say cosine of 2 theta is 1 minus 2 copies of sine squared. That's a second version of the double angle formula for cosine. And it just gives me a relationship between two functions. Cosine evaluated at 2 theta and sine evaluated at theta and squared. And I mentioned that one of the nice things about identities is it gives us options. I can rewrite things different ways. Because sometimes I want to do something to my trig expression, and it's hard to do when it's written a certain way. But it's easy to do when I write it a different way. So for example, taking the square root of 1 minus cosine squared, that looked kind of complicated. It got simpler when we rewrote that as the square root of sine squared. In general, what we did with that example was an algebra thing. We took a square root. We're sometimes going to want to do calculus things, and I'm talking very vaguely here because I realize not everybody has taken or completed a calculus course yet. Some of you are in pre-calculus, some of you are currently taking your first semester calculus. Those of you in 3B who are in second semester calculus know that we'll recognize the calculus thing that I'm going to talk about, which is integrating. Doing that thing happens to be integrating to a square of a trig function, rather tricky. Doing it to just a trig function, evaluated at twice an angle, relatively simple. So what I'm going to do is I'm actually going to take this identity. This is a double angle formula for cosine. I'm just going to rearrange it and solve it for sine squared. So to do that, I would say cosine of 2 theta minus 1 is negative 2 sine squared theta. So sine squared theta is cosine 2 theta minus 1 all over negative 2. Usually the way you'll see that written is sine squared theta is, I'm going to take this negative sign and rather than keeping it on bottom with the 2, I'm going to move it up to the top. And if I multiply the top by negative 1, because I'm moving the negative that's already there, I'm just moving it and associating it with the top, the cosine becomes negative and the 1 becomes positive. So I'm going to write that as 1 minus cosine 2 theta all over 2. This is sometimes called the power reducing formula. We went from a square of a trig function to a slightly more complicated looking expression, but it just involves a single power of a trig function. And that lower power makes it a whole lot easier to work with for the purposes of doing this calculus thing, which is called integration. Okay, excellent. So sometimes that's called a power reducing formula. Sometimes I just refer to that as the double angle formula because it comes directly from the double angle formula. It's a consequence of that. Now I can do something similar by replacing the sine squared with 1 minus cosine squared. So if here was my basic initial version of the double angle formula, I can say cosine of 2 theta is cosine squared theta minus. I can replace sine squared with 1 minus cosine squared. Now, I do have to remember to distribute that negative. So that's going to become cosine squared theta minus 1 plus cosine squared theta. Cosine 2 theta is 2 times of cosine squared theta minus 1. I'm going to just erase this work, but keep that result up. If I were to solve this for cosine squared, cosine 2 theta plus 1 equals 2 cosine squared theta. Cosine squared theta equals cosine 2 theta plus 1 all over 2. These two formulas allow me to rewrite a square of sine or cosine in terms of just a single power of sine or cosine. And that does make a lot of things a little bit easier. Okay. So there are a bunch of formulas here. Everything that's on the board right now follows from the sum formula for sine and cosine. So if you know the sum formula for cosine, you get the double angle formula for cosine. This is the version that falls out of it directly. Throw it in with Pythagoras to rewrite either cosine squared or sine squared in terms of the other trig function squared. And then you can solve for cosine squared or sine squared and express it in terms of just cosine of 2 theta. Hopefully it makes some sense that it's sometimes easier to work with a single power of something than with that thing squared, even if you're not at the point in your calculus career that it makes sense when I say it's easier to integrate this than this. Those of you in 3B, hopefully you can see that yes, it's easier to integrate this than this. Okay, it's the identities that I wanted to go through. I will just mention for graphing purposes, it's useful to know whether trig functions are even or odd. We tend to use that more often when we're graphing than simplifying expressions, although we sometimes do use it with simplifying expressions. So those are other identities that are useful, but I didn't write them out today just because in the interests of time. But I would say what we went over today are probably the most essential ones for your success in these classes. I just don't want to give you a mistaken impression that we covered every single one that's out there. We covered the most essential ones, and fully you saw how just knowing that picture of the unit circle with the triangle in it and knowing the silly story for the sum of sine and cosine allows you to get a whole bunch of identities without a lot of memorization. Okay, so I'm going to stop the video now, but I will stick around if anybody has questions. So if you're here in person, you can feel free to